Okay, so welcome to this next lecture, and so good afternoon to all. So let me just recall that in the previous lecture, what we have recalled this properties about this ring of integers, and then we have also discussed what is so-called these properties about this polynomial ring. And then what we saw in this both the rings, one thing is common, and it is of importance to us to first of all, if you have any element inside a ring, then one would like to factor that element into irreducible factors. And moreover, if the factorization is unique, then it is of practical use. Yeah. And so therefore one is interested to find or generalize this notion of factorization for general integral domains. And so in order to do those things, so what we have defined for a general integral domain, divisibility concept. And then we also defined what do we mean by proper divisor, that A is a proper divisor of B if you can write B as a product of say two elements where both of them are not units. Yeah. And then we have defined the notion of irreducible element in a general integral domain. And also we have defined what is the meaning of associates. Yeah. And so let us start with this, and we will again recall this definition in terms of ideals. Yeah, so let me just again start with this one. And so what we say, so just it is a recall, and this is what I would like to say, that in terms of ideals. Yeah. So in terms of ideals, this divisibility can be understood in terms of containment and other things. So let me just write one by one. So so first of all, U is a unit. Yeah, and this can be defined in terms of ideals as, if you try to look the ideal generated by U, that will be equal to full ring R. Yeah, so this is will be same as the ideal generated by one, and say it is full ring R. Yeah. And the second one, A and A dash are associates. So they are associates means what? By the very definition that we have given, that means so one will be a multiple of a unit. And so in terms of ideals, it can be understood as the ideal generated by A should be same as the ideal generated by A dash. And these things you can prove by yourself and not very difficult. And the third one is about divisibility. So A divides B, that also can be proved in terms of containment, that the ideal generated by B is contained in the ideal generated by A. So here, so let me just say that in a short, one says that this is to divide is to contain. Yeah, to divide is to contain. Yeah, so this is the terminology that one uses for this fact. A divides B is same as the ideal generated by B is contained in the ideal generated by A. Yeah. And so we also defined what is the meaning of A is a proper divisor of B, and A is a proper divisor of B. Yeah. And so this can be understood in terms of ideal as what you can say, that if you look the ideal generated by one, yeah, so that is the, of course, the full ring R, and any ideal will always be contained in this full ring. And so what is the proper divisibility means that this ideal generated by say A is properly contained in this ring R. Yeah. And then this ideal generated by B is properly contained in A. Yeah, so this is the meaning of proper A is a proper divisor of B. Yeah. And so let me just now, so what we have interpreted the earlier definition in terms of ideals. And so now let us come to our original question, and our aim actually is to extend this fundamental theorem of arithmetic for general ring. Yeah. So the aim is to extend this fundamental theorem of arithmetic for general integral domain R. Yeah, for where R, I mean, is an integral domain. And so this is our aim. And if you try to recall, that fundamental theorem of arithmetic contains two parts. So the first part is about the existence of factorization. Well, yeah, existence of factorization of an element, factorization of an element, yeah, inside the say ring R itself. And the second one was the uniqueness, yeah, uniqueness of the factorization, uniqueness of this factorization. And so let us try to start with discussing the existence of a factorization. And so let me just say that what do we mean by the existence of factorization? Means, as in the case of ring of integers or polynomial ring over a field, what we saw that any element can be written as a product of irreducible elements, and the factors are finitely many. Yeah. So here existence of factorization means that one should be able to write a given element in terms of finite number of factors, where after writing that element into a finite number of factors, each factor should be irreducible. Yeah. So let us start. And now we are in a very general integral domain. Part is existence of factorization. And suppose if you take any non-zero element inside your integral domain R, so so the first thing is that if A is irreducible, then it is written as a product of irreducible elements. That's fine. Yeah. Then we are done, no problem. Yeah. And if A is not irreducible, then it will have two proper factors. So if not, then what one can do, that A can be written as into two factors, A1 and B1. Yeah. Now, if A1 and B1 are irreducible, then we are done. We got the factorization of an element inside the integral domain. Yeah. And if A1 and B1 are not irreducible, if A1 and B1 are one of them, at least not irreducible, not say irreducible, then we can again factor each A1 and B1 into further factors, so that A is A1 B1, and A1, for example, is factored into A2 A3, and if B1 factors into say B2 B3, then we have this. And again one will be continuing this process, so one can continue this process. And now the question is that whether this process stops or not. Yeah. So the question that one gets here, one will get stuck about what is the guarantee that so so what is the guarantee, what is the say guarantee that this process stops, that this process will terminate. Yeah. So this process stops. Yeah. So just I would like to ask, do you give an example where this process doesn't stop or it always stops? What is your guess, or do you have any examples? If you have, please let me know, and then we will proceed further. So here we have a challenge, that how to know, or what is the guarantee that such a factorization or such a procedure will stop after finitely many steps. Yeah. If it stops, then we know that for general integral domains we have existence of factorization. If not, then one is interested to find an equivalent condition to uh, 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 to know when this process stops. So if you have any doubts or comments, please let me know, and if you can give an example, then we can proceed further. So now let us try to see that in general this process may not stop, and you will be writing the factors of a given element infinitely often. Yeah. And so the example I think one can construct by themselves, just by so if you take, for example, the standard example that is in this case, is known. Of course, here one is interested to write an element infinitely often, so therefore at least that the element of a ring should contain at least that infinitely many elements related to a given element A. Yeah. And so now what you do that if you look this polynomial ring in infinitely many say variables, f of say x1, x2, x3, and so on, where these xi are related in the sense that say x2 square is x1, that means this ring. So well, you can prove that this is an integral domain, that is not a problem. This uh, polynomial ring in this thing is an integral domain. And what is the relation with all these elements is like that so there is a square root of x1, and then there is a fourth root of x1, so that is x3 square is equal to x2, and that means this polynomial ring contains all the 2 to the power kth root of x1. Yeah. And similarly this, if we write x4 square is x3, and so on. Yeah, so they are related like this. And now if in this ring, if you try to take x1, so x1 by the very relation has the form x2 square, and this x2 square we are understanding as x2 times x2. Now x2 has a x3 square, so we can write it as x3 square times x3 square. And now this again, if we break x3, so if we write it as x3 times x3, and then times x3 times x3, and then x3 is written as x4 square times x4 square times x4 square times x4 square. And so if you can see that this process will not stop at any stage. And so therefore, in general, what we see from this example that there is no guarantee that a general integral domain will have such a property. Yeah. So and one thing from this one can notice that this, if you try to look at the ideal generated by, for example, x1, so note that in this example, note that if you try to look the ideal generated by x1, this is contained in this ideal generated by x2. Yeah, because you can reproduce x1 by multiplying x2, and similarly ideal generated by x2 is contained in the ideal generated by x3, and so on. Yeah. So therefore, as you can see that you get an increasing chain of increasing infinite chain of ideals. So thus we have an increasing infinite chain of ideals. Yeah, chain of ideals in f of this polynomial ring x1, x2, and so on. Yeah. And so therefore now the question is that what is the condition, or under which condition this process will always stop? In fact, I can factor a given element into finitely many steps. Yeah. And so actually what we are going to see that this is actually the abstraction. Yeah, that if an integral domain contains an infinite chain of ideals, increasing infinite chain of ideals, then in that integral domain, one cannot have a existence of factorization. Yeah, so this is the thing, and that we are going to prove in this lecture. So that is the theorem. So let me just write down. So this is example. And so by the way, any questions so far?
No, sir.
Okay, good. So let me start with this theorem. What does it says that we need to start with an integral domain. Let R, so an integral domain, yeah. And then the following are equivalent. Yeah, so by this notation, I mean that the following are equivalent. Yeah. So the first statement is that for every a not equal to 0 inside the integral domain R, and which is not a unit, a not a unit, then we can write. So what we would like to say that A can be written as B1, B2, and so on, BK. Yeah. Yeah. So where BI is are what one should say that irreducible elements of this integral domain R. And the second condition that is we have just discussed that R, this integral domain, does not contain an infinite increasing chain of ideals, infinite increasing chain of ideals. Yeah. So what is the meaning of this? I.e., that this ideal just generated by, say, for example, A1, and here when we say that infinite increasing chain, that means this containment is proper, that A1 is properly contained in the ideal generated by A2, and A2 is properly contained in the ideal generated by A3, and so on. Yeah. So this is the equivalent condition about the existence of factorization inside an integral domain. And so do you know the proof of this, or should I skip? Anyway, proof is not lengthy and it is very simple, so we can actually quickly recall the proof. So let us try to see the first. One implies two and two implies one will be similar proof, so I will be skipping. So let us start. So one implies two means we will assume this first property, first statement, and then our aim is to prove this property second. Yeah. So and usually in this kind of this proofs, one always try to prove the theorem by the method of contradiction, because in the first statement you have given certain finiteness condition and you would like to deduce certain finiteness condition in the second statement as well. Yeah. And so what one does, that suppose 2 does not so what we would like to prove, that suppose that the second condition doesn't hold, suppose 2 does not hold, 2 does not hold. And so what is the meaning of that? That means this integral domain R contains an infinite increasing chain of ideals. Yeah. So this implies that R contains an infinite increasing chain of ideals, increasing say chain of ideals. So that means A1 is properly contained in the ideal generated by A2, and ideal generated by A2 is properly contained in the ideal generated by A3, and so on. Yeah. And this yeah, so therefore what we can see from here, that so note that here, so any ideal of course will be contained in the full ring R. So that means that here we have An, ideal generated by An is, let's say, properly contained in, yeah, this is properly contained in An plus 1, and any ideal is of course contained inside this ideal R, yeah, which is generated by say 1. Yeah, so therefore what we see, that what we see from this, that since it is an increasing chain of ideals, that means An minus 1 is properly contained in An. And if we write this containment in terms of divisibility or factors, so what we can write as this An minus 1 can be written as An times Bn, yeah, where this An and Bn are non-units, because this is the proper containment, and for proper containment this both these things should not be unit. Yeah. And so this is true for every n, let's say, inside the set of natural numbers. And so if you try to write A1, for example, so A1 can be written as A2 B2, And so A2, now by this again, if we apply this thing, so we can write A2 as A3, B3, then B2. And if we apply this process again, so what we see that A3 can be written as A4, B4, and then we have B3, B2. And similarly, if you continue this process, what you see that this uh, A1 have a factorization which doesn't stop, yeah, and which contradicts the fact that one is true. That means for every non-zero element of the integral domain, one will be always able to write A as into finitely many factors. Yeah, but what we see that if we assume that R contains an infinite increasing chain of ideals, then we get an element which can be written into factors which doesn't stop. Yeah, so what we see that, but but this contradicts the property one. This contradicts one, and hence two follows. Yeah, and similarly, similarly you can prove for two implies one, and the method is same that one need to assume two, and then one need to prove one, and then one can again go through by the method of contradiction, that this suppose first statement is not true, then whatever the consequences you will get, that will contradict the second condition. Yeah, okay, so far so good. So this is about actually this theorem ensures that when a given integral domain has the existence of factorization, and that means, and that condition can be interpreted in terms of the fact that this integral domain should always contain means there is a finiteness condition imposed on this integral domain in terms of ideals. Yeah, so that this integral domain should satisfy the finiteness condition, that it should not have an infinite increasing chain of ideals. Okay, so this is the first part where we see the existence of factorization. And well, the second condition actually is about, as you can see, that the increasing chain of ideals. So usually it is known as ascending chain of ideals. So ascending chain of ideals. But here, since we are talking about this existence of factorization, we will say that if one of these property holds, then we say that the R has the existence of factorization. So let me write that thing as a definition, and then we will proceed further. Yeah, that R an integral domain, then we say that we say that uh, existence of factorization holds inside this integral domain R if any of the above condition in the theorem are satisfied. If any one of the conditions, if any one of the condition in the above theorem are true, in the above theorem is true. Yeah, so this is the meaning of the existence of factorization, and since both are equivalent, we can demand, I think, means one condition will be sufficient to say the other thing. And this is the terminology that we have just introduced, that means an integral domain has a factorization if it does not contain an infinite chain of ideals, or the first condition as well. Yeah, and now let us come to the second property, which is the uniqueness part, and then we will be defining what is so-called unique factorization domain. Yeah,
Balesh,
okay, yes sir.
can I say a comment to one point?
Yes.
Can you show the result that yeah.
Yes.
Yeah, so I am just asking students, so all of you, is it result is true for field? Just think about what is a problem or something. So why I'm asking this question is that those people who are feeling that it is little slow, when results are stated, think about different things. Okay, this is one question, right? And so what is the problem with the field? Any one of you?
The field has made it too ideal.
That is okay.
Every
What about
non-zero
the
element is a unit.
every non-zero element is unit. So
Correct.
what is happens in the field? Can you find an irreducible element in the field? Do you have an irreducible element in the field?
No,
No, right? Yeah. So,
every element is a unit.
so every non-zero element is unit. So there are so now ask this question similar to that. Are there any integral domains similar to this? There are there doesn't exist any irreducible element. Of course, field is one example, right? Do you have any other examples where integral domain but there are no irreducible elements at all? Is the question clear to you? तो tomorrow tutorial पे हम दो example देखेंगे आप भी check कर लो. Is the question clear to you?
Yes, sir.
Pick yes if you, it is clear. Question is that can you find two examples of integral domains in which no irreducible element exists? Of course, excluding the field. Field does not have any irreducible elements, right? If there doesn't have, then there is a problem. Okay, yeah, fine. But for field, it is vacuously true. If there is a, so first question, first statement is saying that if there is a non-zero non-unit, then only we are asking. So it is vacuously true. Okay, Balesh, sorry, take care.
No, it's fine. Good. Actually, yeah. At least this example should be, yeah. Means that examples will clear this what is going on in this theorem actually. Yeah. So okay. So let me come to this uniqueness part, and so let me start. So we have in this fundamental theorem of arithmetic, the second part is about uniqueness. And so suppose if you have an integral domain which has the existence of factorization, that means any element non-zero, not a unit element, yeah, inside this integral domain R, if you are able to write as b1, b2, and so on, say bk, where bi's are irreducible elements inside this integral domain R. So bi's are irreducible. And then what we can say about uniqueness? Yeah. So the obvious choices, for example, if you are in the integral domain and if you have say plenty of units, so units may a bit disturb this factorization. For example, if u1 is a unit, then what you can write that this you can write as u1 b1, and then u1 inverse b2. Yeah. And you club this as one element, you club this as second element, and so on bk. And if you have u2 another unit inside R, then you can similarly club u2 with its inverse inside some other elements here. And then you can say that b1 will be different from u1 b1 and b2 will be different from u2 b2. So, and this is the obvious choice that disturbs the uniqueness inside the integral domain. Yeah. And well, and as you can see that, well, they are different but they are associates, that b1 is an associate of u1 b1, and similarly b2 is an associate of u1 inverse b2, and so on. And so therefore what we see that this obvious units creates a problem for uniqueness. And so in the statement of uniqueness, one is tempted to overlook or disregard these units and associates. So therefore what we can say that up to units are up to associates, this factorization is unique. Yeah. And well, so this and this up to units and up to associates also can be means can be disregard or can be skip from the role if one tries to discuss these things in terms of ideals, because in terms of ideals, as we have defined, these associates and units will not come into the picture as we have discussed here, because in terms of ideals they will be the same. Yeah, but anyway, and that goes into a different direction, and where the factorization means unique, and where the factorization holds at the level of ideals, that has a different notion, so-called dedicant domain, and we will come in further lectures, if time permits, what do we mean by dedicant domain. So here we are trying to discuss the factorization in element wise, but dedicant domains are the integral domains where the element wise factorization may not hold unique factorization, but at the level at the ideal level they have unique factorization. Yeah, but here we for the time being we will focus on the element wise factorization, and we will compromise with this units and associates to discuss about the uniqueness part. Yeah, okay, so let me just write down this. So one thing is this, and the other thing, if you try to recall in the previous lecture, uh, uh, in the case of ring of integers or polynomial ring, we have very nice description that we are able to say that these primes pi's are positive primes. Yeah, and similarly we were able to say that this in the case of polynomial rings, we were able to say that these irreducible factors can be taken to be monic. Yeah, here. Yeah, but inside in a general integral domain, so one will not be always to find nice normalizations which will ensure a very particular elements that will be inside an integral domain. Yeah, but in these nice rings, yes, we do have a proper normalization that looks very nice, but of course here we should say uniqueness up to associates or up to units. Yeah, and so with this much discussion, so let me now define what do we mean by this uh, uh, unique factorization domain. Yeah, so we are going to define what do we mean by UFD. UFD, I am writing in short for the notation, a unique factorization domain. So, so we have R an integral domain. Yeah, and we say that R is a UFD. R is a unique factorization domain if the following conditions are satisfied. If the following conditions are satisfied. Yeah. So what are the conditions? So first condition is that that existence of factorization holds in R, holds inside the integral domain. Existence of factorization holds inside the integral domain R. And the second thing is about the uniqueness. And so uniqueness, so let me write down what do we mean by uniqueness. That if you take any non-zero not unit element inside this integral domain R, and if you are able to write the element A as in two ways, that P1, P2, say Pm, and if you write this element A as in another way, Q1, Q2, Qn, where Pi and Qis are irreducible elements, then uniqueness, I mean that then M should be equal to N. So number of irreducible factors in one factorization should be same as in the second factorization, and up to the ordering of the terms, up to the ordering, sorry, is there any question or? Okay, so and up to the ordering of terms, what we can say, as we have discussed, that Pi is an associate of Qi, is an associate of Qi. Yeah, so therefore these factors will be differ, they will differ only by units. Yeah. So this is the definition of unique factorization domains. And so now let me at least give an example of integral domain which is not unique factorization domain. I think the example should come from you. That will be very nice. And then so do you know an example of an integral domain which is not a unique factorization domain?
Z adjoint I root 5.
Okay, what Z? Okay, you are telling that if we take R to be Z, and if you look square root of -5.
Yes, yes.
Yeah, so yes, of course, this is by notation. I hope you know this notation. This is the collection of all elements a plus b square root of -5, where a and b are integers. Yeah, and well, you can prove that is an integral domain with respect to the usual operation of addition and multiplication, which come from, if you think of it as a subset of, say, complex numbers. Yeah. And in this ring, so of course, what are the units? Yeah, so what are the units in R? Well, you can prove by yourself in the tutorial that units in R are precisely this +1 -1. And in fact, if you try to see more general imaginary quadratic extensions, and there you can see that there is a notion, if time permits, we will see that there is a notion so-called ring of algebraic integer. And so for imaginary quadratic fields, and if you try to look at the ring of algebraic integers, usually they will be of this form. And most of the time, units in the ring of integers for an imaginary quadratic fields are +-1. So that's the general result. But in this particular example, one can prove that the units are precisely this +1 and -1. And now, of course, as you can see that this set of integers is contained inside this bigger ring. Yeah, and so therefore the every element of this is an element of the ring R. So 6 is an element of our ring R. And 6, of course, we know nice factorization inside Z, which is 2 times 3. And what we also factor now, 6 can be factored in one more way inside this ring R. Yeah, and that I think is very easy to guess, that 1 plus
1 plus or minus root -5.
right. Yeah, 1 plus is square
1
root of
plus root -5 into 1 minus root 5.
right. Yeah. So in this way, now again, I think it is a question in tutorial that the elements 2, 3, 1 plus square root of -5 and 1 minus square root of -5, they are irreducible elements inside this integral domain R. Yeah, if not, then you can try by yourself to check that these are irreducible elements. And now what we need to check that this now the associates of 2 are +2 and -2, and similarly associate of 3 is +3 and -3. And one can check that 2 is not in any way equal to 1 plus square root of -5 or 1 minus square root of -5. And so therefore what we see that we got the factorization of the element 6 in 2 different ways. And so therefore this violates the definition of unique factorization domain, that the uniqueness part is actually here not same, because up to ordering of the terms, pi is this one of the factors should be the associate of the other factor. But it can be checked here that 2 cannot be an associate of 1 plus square root of -5 or this one. So therefore, thus we see that thus R is not and UFD. Yeah. So therefore, this property in general may not be true for any integral domain, and so these two conditions actually specify and makes what is the meaning of this unique factorization domain. Yeah, okay, so far so good. So now let me proceed further. And so if you try to see that in the case of integers, what we have told that this factorization occurs in terms of primes. Yeah, and here we are talking in terms of irreducible elements, and therefore one is interested whether these two concepts are same or different, and if they are not same, then under which conditions these two concepts, that the irreducible element and prime elements, will be same. Yeah, yeah, so this is the thing that we would like to discuss further, and then our aim is to prove today the another concept related to the unique factorization domain is actually an generalization of this is known as this generalization. I mean to say that nicer integral domain than unique factorization domain is principal ideal domain. So our aim is to proceed towards the principal ideal domain. Yeah. So let me now recall. Anyway, you know this definition of prime element. So if you take an element P, a non-zero element, and of course it is not a unit. So again, it is not a unit inside an integral domain R. Yeah. So we say that P is prime. P prime if P divides this element product of two elements should imply that either P divides A or P divides B. Yeah. So this is the definition. And well, so can you give an example that where an element is irreducible but not a prime? Yeah. And I think hint is that the same example will work here. This example itself will give you the answer. Yeah. So if you try to look the square root of -5, and as in the tutorial it is given that prove that 2 is an irreducible element. Yeah, 2 is an irreducible element inside this integral domain R. 2 is irreducible in z square root of -5, and 2 divides 6. Yeah, and 6 can be written as 1 plus square root of say -5, and 1 minus square root of -5. But you can see that but 2 neither divides 1 plus square root of -5, and 2 neither divides 1 plus square root of 1 minus square root of -5. Yeah, yeah, so that you can also check. And so therefore what we see that in general these two notions, that irreducible and prime elements, are different. But I think in a tutorial you have also an exercise that but this prime notion of prime element is stronger than the irreducible notion. That means in any integral domain a prime element is always irreducible. Now the question is that when an irreducible element inside an integral domain will be a prime element. Yeah. And so that is the proposition that we will quote without proof, and we will of course use this proposition in our further lectures. And so the proof is also not very difficult, and so let us just try to write down that if we take R to be an integral domain, yeah, and suppose that R suppose that the existence of factorization holds inside R, existence of factorization holds inside the integral domain R. Yeah, then what this proposition says, that then R is a UFD if and only if every irreducible element is a prime, if and only if every irreducible element is a prime. Yeah. So in a sense, what does this theorem says? That, well, we have an equivalent condition for the existence of factorization. And what this theorem says, our proposition says, that if you have an integral domain having this existence of factorization property, then the uniqueness property is equivalent to saying that the every irreducible element in the integral domain is prime. That means inside this integral domain, if inside any integral domain in which existence of factorization holds, then uniqueness is equivalent to saying that irreducible elements and prime elements are same. Yeah, so this is a somewhat characterization or equivalent condition about the uniqueness that we have discussed in this part here. Yeah. And so I will skip the proof of this proposition, but of course it is also not very difficult. But for the time being, our aim is to somehow proceed further and prove certain results about the connections between these principal ideal domains and unique factorization domains. So by the way, any questions so far?
No, sir.
Okay, fine. So now let me again just recall, anyway, you know the definition of principal ideal domain. Yeah. So let me just recall that an integral, so here R an integral domain, and so we say that this integral domain R is a PID if every ideal is a principal, if every ideal in R is a principal ideal, in R is a principal ideal. And principal ideal, I mean here that every element, every ideal is generated by a single element. Principal ideal, I mean that it is generated by a single element. Yeah. So this is the PID is the short notation for this principal ideal domains. And so what I would like to prove a theorem, or what should say either a theorem or a proposition, that so let R be a principal ideal domain, then so the condition that we have just discussed about the as finiteness condition for ideals in this theorem, that R does not contain an infinite increasing chain of these ideals, actually is one of the important property that these principal ideal domains have. Yeah, then R does not contain an infinite increasing chain of ideals, infinite increasing chain of ideals. Yeah, so this is an important property, and so therefore this will automatically say that R any principal ideal domain has a existence of factorization property. And then now the question is somehow what about the irreducible elements? And I think it is again a question in the tutorial, that inside a principal ideal domain every irreducible element is a prime element. And therefore, if you combine this theorem along with the fact that every irreducible element is a prime element, then this proposition will say that every principal ideal domain is a unique factorization domain. Yeah. Anyway, I will write that as a separate theorem, but just it was a quick overview that what is the actually use of this theorem. And in fact, in particular, it proves that every principal ideal domain is an unique factorization domain. Yeah. So let us try to prove this theorem. And so what we need to, so here we have given the property that R is a principal ideal domain. And again, the proof is by contradiction. Proof is by the method of contradiction. That means we need to assume that R contains an infinite increasing chain of ideals. Suppose, so let me just write down that suppose there exists an infinite increasing chain of ideals inside R. That means A1 is properly contained in the ideal generated by A2 is properly contained in the ideal generated by A3 and so on. So here this containment is proper. Yeah. So now here what we can do that we can form a union out of these increasing chain of ideals. And so if you try to write it as I from 1 to infinity AI, and if you call it as a notation, say capital I, then well, in general, union of two ideals may not be an ideal inside inside a ring, but you can prove that if you have an increasing chain of ideals, then one can prove that the union of ideals is in fact an ideal. Yeah. And so I is an ideal of R. And it is just because that you can prove that if you take any two elements inside this union, then these two elements will lie in one of the ideals and use the property of that ideal to say that U plus B lies inside that particular ideal, which lies in particular this union. Yeah. And so, and similarly, the other property in that scalar multiplication will also can be proved in this increasing chain of ideals. Yeah. So that is a that should be proven as a separate lemma, but it is very easy here. And now what we have given that R is a principal ideal domain, and so we have very big union here, and we are able to write, we are able to generate this big ideal by a single element, and that is actually the crucial point to prove this theorem, that once you write this union as a single element, so since R is a principal ideal domain, R is a PID, this implies that I is generated by a single element, let's say B. Yeah, B belongs to the integral domain R. Now what we see that since B belongs to B is exactly equal to this union, I from say 1 to infinity AI, so B will lie in sum of AI. So this implies that B belongs to ideal generated by AN for some n. Yeah. And now since it is an increasing chain of ideals, what we see that this is an increasing chain of ideals. So therefore what we see that B belongs to AN, ideal generated by AN, sorry, which is properly contained in the ideal generated by AN plus 1. And this ideal generated by AN plus 1 is properly contained in, let's say here proper containment is the union I from 1 to infinity ideal generated by AI. And this union is again is same as the ideal generated by B. Yeah. So therefore what we see that this and here also one can write in terms of containment is ideal generated by B is contained in A ideal generated by A. And so therefore what we see that AN is equal to B, thus from this thing what we see that B ideal generated by B is contained in this, and AN ideal generated by AN is contained in B. Therefore what we see that ideal generated by B is same as ideal generated by AN. And similarly what we can prove that this ideal generated by B is contained in AN plus 1, and ideal generated by AN plus 1 is contained in the ideal generated by B. And so this is again equal to AN plus 1. So therefore what we see that from this stage onwards, this natural number n onwards, the ideal generated by these ANs are same. Yeah, AN and AN plus 1 and so on. But this gives a contradiction to the fact that we have started with an increasing chain of infinite increasing chain of ideals. Yeah, which is a contradiction, and therefore if we get some contradiction, that means we have done some wrong things, and that wrong thing we have done in the very initial stage, that we have assumed that the we have an infinite increasing chain of ideals. Yeah, so thus what we see that thus R does not contain an infinite increasing chain of ideals. Yeah, so therefore, and hence this proves this proposition. And so let me again write as what I should say as another theorem, that UFD implies, sorry, so since I have written, so let me write in this way: UFD is implied by PID. Yeah, so let me and I think proof I have already told that this the first part, existence of factorization follows from above theorem that means this theorem as well as this theorem where I have proven this what is so called, yeah, so let me give a name this as, for example, theorem A, and if you give it as a name as theorem B here, so if you give as theorem B, then what we can say that this existence of factorization follows from theorem A and theorem B. And the second uniqueness actually follows from this proposition that we have quoted here. This one follows from the above proposition, and the fact that inside a principal ideal domain, every uniqueness follows from the above proposition, and the fact that if, inside a PID, inside a principal ideal domain, and the fact that in a PID every irreducible element is a prime element. Yeah, and so therefore what we see from this, that principal ideal domains are actually always a unique factorization domain. And well, the other way, this part converse may not be true, so this part may not be true in general. So can you give a quick example where this converse is not true?
Radix.
Okay, so yeah, if you look at this polynomial ring R to be, say, this polynomial ring with integer coefficients, then well, we don't know, by the way, that is a unique factorization domain. But anyway, we will be, one of our aim is to prove that ZX is a unique factorization domain. Yeah, so the proof is not as easy, but anyway, so let me just write down to be proved. It will be proved in my coming lectures, to be proved later, that I will prove that this is a unique factorization domain, but it is not a principal ideal domain, but R is not a PID. And that's obvious because you know, maximal ideal inside this polynomial ring, which is not a principal ideal. Yeah, and that maximal ideal, I think if you try to look at any prime PR, for example, if you take 2 and the ideal generated by X, then this is an ideal in R which is not principal. Yeah, which is not principle. Yeah, that you can prove by yourself. And so therefore, at least today's lecture, what we have seen, the notion of existence of factorization, and then and we have saw that this existence of factorization imposes certain finiteness condition on the integral domain. And then what we saw further, that uniqueness is somehow inside integral domain where existence of factorization holds is somehow equivalent to the fact that the irreducible and prime elements are same. And then we saw a nicer extension or nicer integral domain, which is principal ideal domain, are always a unique factorization domain. And also what we saw that this in general unique factorization domains are may not be a principal ideal domain. And so now I would like to stop. Thank you very much. So we will meet in the next lecture and we will continue Euclidean domains.